a bit more. Okay. We have lots of materials to cover today. A lot of it is very, very classical material in computer graphics, but I'll teach you a few things about mirrors and how to compute mirrors, and that would be less intuitive. Barycenter coordinate, we talked about it about 50 times in this course. I have some pixel P that is a fragment. The vertices was given as a separate program, and information, as far as we know, are all given only for the vertices, like location, like color, like normals at the vertex, which might or might not be the real normal. We'll see why it's beneficial to cheat about what's a normal. Of course, position in 3D, usually position expressed in homogeneous coordinates. I'll remind you what's homogeneous coordinates, but and so on and so forth. And now the fragment programming, pixel programming, is a program that I'll say, given that I have some point inside the triangle, the gizmo underneath the hood will compute for this point what are the weights given that its location of this pixel. And for each and every pixel in this triangle, you don't need to write the loop yourself. It will all, well, that for a generic pixel, take the 3 weights, how the weights are defined. You don't need to do it manually, but for your information, of course, and for the final, the location is look at the area of the triangle, look at the area of the 3 triangles that this point on the pixel, for example, a pixel, this point on the triangle, sorry, for example, a point on the projection of the image plane, look at the area of these 3 triangles that this point defines. That defines the weights. And now I know that if I want this point to be on the triangle, then convex combination, the sum is 1 and they're all positive. All weights are 1 and they're all positive. The sum of weights will place this point on the plane that the 3 vertices define and inside the triangle. It also will be a good way to ask if a point is inside the triangle or not. If the sum of weights is larger than 1, it means that my point is outside the triangle. Exactly the same example that you saw with a billboard that was, once again, homogeneous coordinates. It's just more natural, at least to me, to think about it when it's rectangle instead of triangle. But the concept of area divided by the global area is the same. So that's how I generate a point physically on the plane of the triangle, hopefully inside the triangle itself. And using these weights, I also interpolate every other properties that I have in mind. And we're about to get to the hardest point of this course, at least for me. Robert, because the microphone died on me last time, drop us an email if there are any problems hearing me, because it happened.
It was working fine.
Yeah, last meeting we didn't have warning signs. Okay, approaching the challenging part of the course. So we will work, and you will work on homework 3 on triangular meshes. Surfaces that are defined by a few triangles glued to each other, possibly a lot of triangles. You'll have one such object, and it will be defined by an object file that I'll tell you in a second. What are the normal formats of objects file when I want to tell you about triangular mesh. Triangular mesh would be a surface, like a skin. Hopefully, topologically, that makes sense, not a Klein bottle, not a Mobius strip, hopefully something that makes sense geographically, and consists of one triangle stuck to another one, stuck to another one, and so forth. And I want to create, you want to create, or you have to create shading in homework 5, specular and diffuse shading on these triangles. You'll have a sun, like in homework 4, and a lot of the things that WebGL will be happy to implement for you. But you still need to know how diffuse and specular works. And at the moment, assumes that every triangle by itself is uniform in its color. The whole surface, let's make it stronger even, the whole surface, the ambient color, RGB, is the same for each and every surface. It doesn't, but there is still light involved in it. So different triangles should look differently depending on if the triangle points towards the light, the triangle is with angle to the light. Everything is true also if the colors are not uniform, but for simplicity. Let's do it with the colors. So I want to, at the moment, just to think about diffuse shading. Diffuse meaning that your location as a viewer doesn't matter, just the direction to the light. Specular would be that it behaves kind of more as a mirror-like, that we'll get to in a moment. So algorithm 1 will say, look at the triangle, look at the cross product of the three vertices. The cross product is a vector that points orthogonal to the surface. And if you are handling the triangle properly, it will be the normal that points outward. I'll tell you in a bit what I mean by the treating the triangle properly. This normal is point outside of the surface. And now I have the direction of the normal. I have the direction of the light, do the cross product. And that would be the beautiful result that I'm getting. So I'll quote my son that when I practiced on this class and ran it through him, he's 14, and he said, oh, that's very similar to what I read in Blender when I studied it, but they said you have complicated objects. You can put a lot of very tiny triangles, but then it will run forever. Instead, put few triangles, but play with the shading, so it would look smooth and high resolution, even though the underlying set of triangles that defines it is very limited. And the same advice applied for you. So you see it even with the light, but, and presumably you've seen it before, but it's clear where there are triangles in this surface. Right. Because why does it look so discretized ugly? Why they are so much highlighted? Because what do I do per each triangle? The color of the whole sphere is the same. The normal of a single triangle is the same for every point on the normal. I cannot change this fact. The normal of the triangle is the same for every point on the triangle. Triangle is flat. Implying that the intensity, the effect of the diffuse shading on this triangle would be uniform for every pixel on this triangle. And it's different from every nearby triangle. So that's flat shading. Very clear that it's attempt to be a sphere, but a very unsuccessful discretized attempt. Low resolution. Just to remind you, diffuse shading, how does it work? You have some coefficient that depends on how much red, blue, green you have on the surface of the object. In the homeworks, you can use it as the ambient color, times the dot product, that is a cosine of direction to the light and direction to the end direction of the normal. How these two angles refer to them. If this angle is 0, then you are getting this number to be 1. And if the correct normal points up away from the light, that is, it illuminates the back side of the light, then this number is -1. And when you take the maximum, of course, you get no light, maximum of 0. But in general, you're doing the cosine. That's what we want it to look like. And that's that would be the result of flat shading, just higher resolution. And that's a bit better, and even a bit better is Phong shading. So I said that there is a challenging part, which would be for me to say Gouraud, which I believe is how the web told me to pronounce it, Gouraud shading. Really, Gouraud shading. And versus Phong interpolation shading. It's the same person, but it's not the Phong simulation of a specular shading. Two different things. That's a Phong interpolation scheme. They're related, one can use for the other, but we're talking about the Phong versus Gouraud versus flat. So flat shading, every point on the normal, every point on the triangle has the very same normal. That was step one. And actually, you'll find textbook that will say there is no Phong shading. Gouraud shading is already captured. Most of what we have under the Phong shading completely, so we'll just call it Gouraud shading. So what should I do with this triangular mesh? Part of a triangle. You have a C. So you see one triangle. It's just a quad. Think that I don't care. And it's neighboring another triangle, and it's neighboring another triangle. You know. So an edge here is an edge between two triangles, and each one has its uniform normal. But I want it to look flat. Sorry. I don't want it to look flat. I want it to look smooth. And shading is a great way to create this effect. How can I do it? By cheating about the normals, or imagining that's maybe a more mature way, is we thought about images as a result of a sample of some continuous domains. We have infinitely many details in this room, but when we take a picture, we only sample it in some discrete set of points, and that's the values that we are getting. Let's use the same philosophy about here is a sphere, but it's the best sphere that I can draw, and I sample it, or downsample it, or synthetically generated it only in some points. So here are my triangles, just 2D, 1D triangle, just one piece of the triangle. But how are the real normals of the sphere looks like? Well, if I move on the real normal, on the real surface, the sphere that defines everything, the normal changes continuously. So somewhere if I'm in the middle of a big triangle, probably that's the only triangle that determines the normal, but as I'm moving from one triangle to the next triangle, the normal should change. So what my issues with normal at vertices? That there is no normal. You need a continuous derivative, continuous at each vertex, which you do not when you have such a sharp change. It's not continuous. So let's fake. Let's assume that we do have the original surface, at least near the vertex. And if we have this original surface near the vertex, how should these normals change? Should be somewhere determined by this triangle over here, should be determined by this triangle over here. Now they should move continuously, where what would be, if I had known, what would be the normal at the vertex V, V1? It would be somehow the average between N1 and N2. So the normal at V2 would be N1 plus N2, the real normal, 90 degrees normal, but average them. In this case, there are two of them, so the average is divided by 2. And by the way, they are all vertices, so when I sum and divide, unless they are collinear, they probably don't result a unit vector, so I'll just think about it. To simplify, I'll just work about the direction, but remember that each time that you are doing it, you want to normalize the length, make it a unit length. but I will not bother with these details right here. Back to my triangle over here, and here is this triangle CD, just an edge in the 2D case, the normal to CD, another edge BC, the normal to BC, 90 degrees over here. What would be my fake normal at the vertex? The fake normal of the vertex would be the average of these two normals. Get it? So the normal at a vertex, also shown over here, is the average of these two normals. 3D life are slightly more complicated, slightly more complicated. Three surfaces, three normals, one normal, another normal, another normal. What happened at the vertex? It's still the average of these three vertices, of these three normals, just it's divided by 3, not by 2. Make sense? Take this normal plus this normal plus this normal, and we are in the step of interpolating or faking the normals at the vertices of the triangular mesh. Again, I'm trying to generate fake normal at the triangular mesh. I need it both for the Gouraud and for Phong interpolation. I need the normal at the vertices. Now, in triangular mesh, I might have a vertex that, in turns, is adjacent to, like, think about a pyramid. In a pyramid, I'll have the top of the pyramid adjacent to 4 triangles, right? And possibly many more in other spheres. So each one of them defined its own normal, and 1 and 2 and 3 and 4 and 5 and 6. Look at this set of triangles. You'll have to do it in your in homework 5. Look at this set of all the triangles that are adjacent to this vertex. In this case, there are 6. Sum up these normals, and divide, in this case, by 6. And, of course, remember that it's unit length. So now you have the normal to these vertices. I created average of NC and average at the vertex B. Now, at this point, Gouraud and Phong separate a bit. Gouraud says you have the very normal at this vertex, which is in turn, you have the normal at this vertex, which is in turn different than the normal at this vertex. So the light is the same light. The distance to the light didn't change by much, but the normal of the real triangle didn't change at all. But the two fake normals, definitely have different values. Apply the formula that we just had for computing the cosine, see it also over here, at this vertex and at this vertex. And the color or the intensity will be different because these fake normals are different. Okay, and now how do I create, going back a few slides, how do I create, I have the new colors at each one of the vertices, because even though it's the same triangle and it has one unique normal, because this triangle has neighbors, I have different fake normals at the 3 points. Applied the shading effect, both specular and diffuse. Ambient doesn't care, but specular and diffuse does care about these normals. Use them to create a shading at the 3 vertices. Now you have the color and intensity of the 3 vertices, and let the gizmos of the fragment programming, pixel programming, to do the interpolation between them. You just need to specify in WebGL that that's what you want it to happen, to interpolate the colors. And that already breaks the flat shading. Okay, no more black air, no more flat shading. That already will create a much smoother surface. But you can go better than this. And especially, let's think about a big triangle, and let's think about specular shading. I can definitely do the specular shading in the same way by faking the normals, but for specular shading, there is also the viewer. Light, viewer at this point, and look at V1 with its fake normal. Either remember at which point do we have the specular spot, the white part will appear. It will appear at the point where you have perfect reflection, more or less. Perfect mirror. Now, I don't have any specular spot at V1, nor at V2. Now none of them has this white spot. That appears because the fake normals don't behave well with as a perfect mirror. That if I put a perfect mirror here and a perfect mirror here, this viewer will not see the light, neither by this mirror nor by this mirror. This mirror will do, but I don't have it. Fong says, OK, make smaller triangles. Grod says, make smaller triangles if you want to do it. But it's not stable, even in this case, especially if you want specular. Fong said, OK, here is a solution for you, and it will be a bit more computationally expensive, but you'll get much better results. And as I said, you sometimes will find this algorithm under Grod altogether. So what are you doing? You will compute for every pixel its shading individually using a fake normal per every pixel. That is, I'll apply the diffuse and specular formula for each and every pixel. Again, that's parts that you're pushing into the fragment programming. But how do I get this approximated normal? I'll use a barycentric coordinates. Again, you don't need, it will just happen for you. Let's say that that's what you want. Remember that you might not get a unit length vector, important. How do I create this approximated normal? It's just barycentric, which is just linear interpolation. For every pixel, which direction is this approximated normal? It's just, we have the weights are 1 minus t and t. That's the contribution of the two vertices, no matter what I interpolate. In Grod, I interpolated between the colors. In Fong, I create for every vertex, for every pixel, I create its own fake normal, and I'm completely cheating. I know what is the real normal of this triangle, and it's not the fake one. Most cases, it will not be the fake one. Nevertheless, I will use the fake one to compute the shading, and then I will get a very smooth surface. And in addition, if you care about the specular effect, then it's not necessarily exactly the real point that you'll get the perfect reflection, the perfect mirror, the specular spot here. It might move a bit, but there will be some pixels on this triangle for which the normal will determine perfect reflection. So, right, because the normals do change across this triangle. So you will see the beautiful specular spots over here. So these will be the results, actually, of specular spots when you're using Fong, when you're using Grod, sorry. And I think that it's noticeable by eye, even with this crappy projector. You see that there is a specular spot, but it's broken in a very unnatural way. Fong model, more expensive. You need to compute a fake normal, approximate, interpolated normal for every triangle. but the specular spot looks much more rounded and much more real. And all of it when we are using a very low resolution of the geometric part. Questions? Classical example for a final midterm, differences between Gouraud and Fong. Advantage, disadvantage. Okay. So we had linear interpolation, like billboard, bilinear interpolation. We also used bilinear interpolation as an anti-aliasing. Some of you used it as an anti-aliasing when you had a pixel between several new pixels after translation between several existing pixels, kind of a alternative to convolution. That is just the idea that inside the billboard, the linear interpolation is not, or bilinear interpolation is nothing but representation by alpha, representation by beta. And every point I can represent by as just the representations that you saw. On the billboard, here are the formula for a sphere. Here is a formula for a plane. But summing it up. What is a triangle? Every shape that you can represent as alpha times 1 point plus beta times second plus gamma times third, and alpha, beta, gamma are in convex combination. Another way to write this triangle, I'm just arranging alpha, beta in a way that makes a bit more sense. I have this triangle, and the very same triangle, and every point of it will be here is A, here is B, here is C. And if you want to go to some point inside this triangle, first go from the origin to A, go to A, and then add some amount of going by beta amount in this direction, and add to it some amount gamma times what? This direction. So this would be C minus A times gamma. Very similar to the alpha and beta that we had earlier, except that it's a bit easier when these two vectors are orthogonal to each other. Okay, just to review. Triangular mesh. That's how graphics works. All your graphical model works either by polygons, for example, triangles, or work by voxels. Medical data would like voxels. You'll get a grid that consists of, instead of pixels, voxels, like 3D grids, and some information about each voxel. Okay, but let's talk about triangular mesh, probably the most known part. Lots of triangles in the Buddha statue. Remember a triangle? If you're looking at the triangle on the mesh, I'll give you we'll keep if the mesh is properly given to you, then when you're looking at the triangle from the outside, its vertices appears in a counterclockwise order. The same three vertices, we discussed it many times, A, B, C, look at them in a counterclockwise order. I'll replace the same triangle, do the cross product of ABC, the same three vertices, but now they'll go in the normal. Which implies that if that's the order ABC, that you'll find them in the input. And the agreement would be that if you define the normal as B minus A, one vector, C minus A, another one, I care about the sign in both cases, and do the cross product in this order, then the normal will point outside of the shape. If I gave you ABC in the object file, and the object file is free of bugs, then take each one of the triangles and do this gymnastic in this order, and the normal will point outward. And then you know if you are seeing this triangle or you're watching the back face of this triangle, but just do the dot product of the direction to the triangle and the normal, the outward normal of this triangle. Don't confuse that it's very much related to our right hand part. Triangular mesh, it has vertices, edges, and faces. In general, it could be any polygons, but more convenient when it's triangles. Every face will be a triangle. And the surface would be piecewise planar. Like you can take big chunk of the surface and somehow stretch them and project them and place them on the table, and they will look like a normal surface. That's if your object file is OK. How come it's not OK? Because maybe you scanned the data, and then you used some algorithms to snap vertices to integer coordinates. Maybe you were missing data. You're not sure which. You scan the object via your laser scanner, laser 3D images. You have a cloud of points. You created the surface. And you didn't do it properly because resolution wasn't high enough. And there are various errors. And what you hope to be a surface, the skin of the object, is not. So how come it could be not a nice surface? We'll get to it. Here is a simple mesh, bunch of triangles that will create a cube. Vertex, vertex, edge, triangles, and so on. And I need to tell you about all of them. Is this planar object? You can make it a planar object by itself. It doesn't look like it, but I can make it a planar graph using the orange algorithm. Orange algorithm says that if you take your orange, blue-orange in this case, put one finger over here in the skin, one finger over here in the skin, like the skin, and then you are peeling the skin over here until it becomes flat. So if I'll take the cube and I don't change which vertex connects to everybody, that just stopped being straight, but that can be fixed later. I just want to place the whole skin on the plane. It's doable. That's kind of the topology. So it's pretty much a planar object, but there are plenty others that are not. Mesh topology versus mesh geometry. There is a difference between them. It's kind of a heavier question, but for our course, we can give a few very simple definition. The geometry will essentially be determined by where do I place the vertices. Once I told you exactly the location of the vertices, what we call the geometry, we are done about it. Can I create from just knowing the vertices the whole surface? Probably not. There are algorithms to reconstruct it, but I might. But it's much more convenient that I'll give you a lot of other related data, which are the topology, namely, there is an edge between this vertex and this vertex. An edge neighboring relationship would be part of the topology. If I'm standing on a vertex in 3D and look at a vertex and look at all the vertices that is adjacent to it, that there is an edge to the other vertices, at which order do they appear? That belongs to the topology. Okay, what are the triangles? At which order these neighbors appears? That's related to the topology, less on the geometry. But these borders are could be quite different. Right? Same geometry, the same cube, different topology. I said the neighboring relationship between the vertices different. At this cube, this vertex is connect to, sorry, this guy and this guy have the same geometry. The vertices could be arranged to be in exactly the same place. Corners are in the same corners, but very different set of triangles, even though the vertices are the same, and very different topology. It's not a sphere-like anymore. It has holes and handles inside. OK. So essentially, we want our surface, if it's free of errors, I'm going to scan a bit through these slides, to be OK topologically. Why? Because I might send it later to my 3D printer in the good case, or to my CNC machine, or create a casting mold, and I don't want to discover that there is a hole in the middle of the object that what I thought would be a solid object happened to be just the skin of the object, and it's completely hollow. It's pretty expensive operation when you're designing, say, engines or casting irons. And there is a lot of money in doing it robustly because people suffer badly from such numerical issues. And geometrical computation in general is prone to be errors. You have a lot of operation like take a big number, divide by a very small number, and based on the result, do either this part of the algorithm or that part. And when you divided big number by small numbers, let's say to ask where two segments meet, if at all, it's very likely that very close segments determining exactly the intersection points between two very close segments with very small difference between them, it's very easy to make mistakes that they don't cross at all, or that they cross but very much to the right or very much to the left, the opposite. Why it's so easy to make this result? Because you have division of large parts versus small parts. It all relates to robust computation. Less relevant for this course, but good that you'll keep it in mind. When you see the mesh, what do we expect it to look like? Look at a triangle, look at the neighborhood of this triangle. It should look like a planar object. Maybe it twists a bit, but you should be able to straighten these triangles and put them on the table, and they will create, essentially, here is a polygon notation that worth noting. This is a simple polygon, or simple, or a simple polygon, and it is A, connected, and B, it is simply connected. You can place it on the surface. There is a clear, unique boundary. The boundary forms a nice curve, single nice curve. Everything inside this curve, inside the face, is everything inside this curve belongs to the shape. Everything outside this curve is not belongs to this curve. What is connected? Look at every point inside the shape. You can find some path, some way to get from one point to any other point, while all your path is inside the shape. I'm not saying that it's convex. It doesn't have to be necessarily a straight segment, but you can find it. It is connected. What is simply connected? Let's show you what is not simply connected. I take from the polygon this hole in the middle, and I extract this part. That will make it, every 2 points are still connected. It can go from here this way or this way. What is simply connected? Simply connected formally will say, take 2 points, or take any closed curve which is fully inside the shape. Everything inside this curve that you just drew should be inside the shape or not. That's simply connected, no holes. That's what we hope to be. Trivia question, is Tucson, the municipal region of Tucson, is this connected or not? And the next question is simply connected.
No, is it called South Tucson?
South Tucson is a city of its own municipal value, which is completely inside Tucson. Okay, so that was an example of surprisingly not simply connected. And as long as everything have nice topology, There are no artifacts in the rendering. There are no artifacts in the manufacture. Bad example, without changing the geometry, the same geometry, but now here are 3 triangles that meet along an edge. It's not planar anymore. It's 3 triangles that shares. It's fine for 3 triangles to share a vertex, but things start to be strange when you have 2 triangles and another triangle that stick somewhere in between. So a decent OBS file will not contain such cases. Not a manifold. That's also not a manifold. If these 2 guys want to connect to each other, there should be some nice connection in between that consists of triangle by itself. If it's just a vertex that is common to these 2 shapes, it's is alarming sign of opening yourself to various geometric errors along it. So that would be a non-manifold. And it gets better and better. I can take the same set of vertices, same geometry, but now part of the white of the Cayenne triangle actually stacks inside the other triangle. They penetrate one into another. Definitely not planar. Again, assume that does not happen. Okay, manifold with boundaries. You see a few that are okay. A vertex can be adjacent to a few triangles, but now these triangles should appear contiguously around the vertex. Issue starts to be if I tell you that this vertex is adjacent to a few triangles, but they are not one after the other. I cannot walk around these triangles, stay only between them, and just create the tip of the mountains over there. So that's another bad example. Fancier definition of topological part is that I want the surface to be nicely oriented. I told you that if I walk around a triangle in a counterclockwise, it's normal. If I walk around the triangle in a counterclockwise, it's normal is outside. Which would mean that if I walk from one triangle to the next one and walk around this triangle in the counterclockwise direction, the normal should make sense. They should be out, both pointing to the outer part of the shape. And I heard about a father of a kid that was a math professor and had to give an active class to the kindergarten of his son and of his child, and he gave them all Möbius strips and asked them to paint it with 2 different colors. But to paint a Möbius strip with 2 different colors, the inner side in one color, the outer side in one color. Give it a try, it doesn't work very well. In this case of the orientation, it would mean that I'll try to orient all my triangles pointing to the outward with the same part, except that as I'm going back to the triangle that I started from, its neighboring contradicts its original neighboring. Okay. Here's the simplest representation of a well-behaved manifold or triangular mesh that are want to do. So there are many reasons that you want to make sure that a vertex will be stored only once. To tell you what the vertex of the triangular mesh carries a lot of information, starting by its location, 3 floats or double numbers, with colors, with various other parts. And as numerous people studied the hard way, is if I said everything is pruned for numerical error. Here is my vertex V1 that belongs to T, and here is the same vertex V that also belongs to the triangle T2. And let's say that when I store t, I keep this vertex, and let's say that the coordinate of this vertex is 1, 1, 1. That's the coordinate of this vertex. And it happens, numerical error, that when I write t1, the same vertex v appears as 1, 1, 1. And now I stored t2, and the very same vertex v is now 0.9999, comma 1, 1. And now you try to manipulate this manifold, and because of this numerical error, it actually turns out that your shape is missing a piece in the middle. You wanted to cast a sphere. Instead, you cast just the skin of a sphere with hollows with holes in the middle. Bad idea. So, and also, vertex carries a lot of information. So, rule of thumb, a vertex is stored only once. Even though a vertex might be adjacent to a lot of triangles, even though a vertex might be adjacent to a lot of triangles, pyramid, I will store all the parameters of the vertex only once. Now, the basic operation that I want to ask is, given one triangle, who are the vertices that determine this triangle? I need it for my data structure. Next information is, given this triangle, who are the neighbors? And giving an edge of the triangle, who are the neighbors of this triangle? Given a vertex, who are the triangles, might be many, that are adjacent to this vertex. Some of these parts I'll answer today. Some of these parts will wait a bit when we'll discuss a data structure for fastening, for improving our operations. But at least these are the basic operations that I need, and here is a very basic data structure that you'll find in OBS file. Triangles, there might be a lot of other informations coming up, but to start with, I'll tell you what is the location of the vertex. It might be 3 parameters, it might be already 4 parameters because we want it in homogeneous coordinates. So, important, a vertex will appear only once, and I need an array of all the vertices. Now, here is a bad example. Definitely, I'll store for every triangle, I'll store the coordinates of the vertices that make this triangle. That's a bad example, not a good idea. Here I stored for every triangle the location of the 3 vertices defined. It makes it a bit faster when I have the triangle, find all the vertices that is adjacent to. That's slightly faster, but it opens me to so many other bugs that I prefer not to. These are the problems that are hinted over there. What should I do instead? One array would be the array of the vertices. Vertex 1, vertex 2, vertex 0, 1, 2, 3, and so on. Each one, so the coordinates of each vertex and the metadata, color, normals, etc., stored once per vertex. Good. What is the other part of this data structure? Here's a list of triangles. Triangle 0, triangle 1, dot, 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 until the last triangle. What do I store per triangle? I store the indices. If you like C, think about it as pointers into this array. If you don't like C, think about it as just the indices inside this array, just a bit slower, of where is, I said that triangle 1 contains vertex 1, vertex 3, and vertex 2. And by the way, in a counterclockwise order, always. And now if I want to actually render this triangle 1, I have to go to the array of vertices and fetch from it where the location of these vertices actually belongs. So a vertex stores the position, and a triangle contains the three vertices, but only the indices of these three vertices. These are int or pointers, if you like, see, if you'll do it in OpenGL. Make sense? Important, a vertex is stored only once, triangles in a counterclockwise order in a normal shape. Now, we will see variants of this data structure that on top of it also adds for an edge who are the triangles that are adjacent to this edge. Not necessary for homework 5, could be expedite a few things. We'll in computational geometry, and I'll mention some simpler variant in this course, a data structure called doubly connected edge list or double wing data structure makes more complicated queries also very efficient. Like if you think about setting the data as so, knowing about this vertex, if I want to know what are if I know about this triangle, what are the triangles that are neighboring along the edge BD, I need to scan all this array until you'll find a triangle that has BD in it. If that's all I stored, then it's very minimalistic, quite compressed, but and meaning you cannot compress it much without losing information. There is no redundancy, but queries that are outside just a single triangle are a bit harder to compute. Not relevant for homework 5, but we'll study more efficient data structures. That includes also who are the neighbors and so on. Neighboring triangles, neighboring edges, again, there will be a question of what do I store per edge? What do I store per vertex? I can go to how do I avoid storing the same information twice, which is risky for various reasons. It's redundant, it wastes space, and much more important, you have the concurrency issues. You're just in the process of modifying part of the data, but didn't modify the same triangle on the other data structures, and you have two different versions, and it usually end up in tears. Okay, and now given this mesh, you have the colors, and you can interpolate them. You can, and that you need to do in homework 5. In using the CPU, you'll assign for every vertex this approximated normal, which is defined by the normals of the triangles. Now, you don't have the normals of the triangles, so you'll need the cross product to compute the normals for every vertex. The normal of the triangles, and where does it point to, and what it's averaged was. But from this point, you are off to go. Just ask the shaders use barycentric coordinates. You don't need to ever worry what are these barycentric coordinates. Yeah, we already talked about it, that diffuse shading will work well better in this way with reduction. Here in the slides, and so on. Once again, in an object file, when you are looking at the surface from the outside, you should be able to orient, or it's given in a counterclockwise orientation of every triangle when you watch it from the outside. So backculling that we'll study very soon is very easy to do. But there is plenty of more data structures that we'll touch on. Let's talk about how do we create 3D effect in geometric shapes. I want to create the idea that these triangles, these polygons, are living in 3D, and for this I need to solve the very, very hard problem, computationally very hard problem of hidden surface removal. Part of what gives us the intuition of how are they arranged in 3D space is that you see that the blue occludes part of the red. Okay. That's really, really important to create the 3D shape. Okay, so hidden surface removal problem. I have a set of polygons in 3D. I have the viewers. And I want to create a two-dimensional image of these projected polygons. And of course, only what the viewer sees from the triangles needs to be represented. I hope that you'll make videos out of homework 5. By the way, nice, cute idea for the videos that you can create is move the camera parameters. It will all run very, very fast. Running time will not be an issue now with WebGL. All the horrendous things that you have to do in homework 3 and 4 to study, you will avoid. There is a little price that you are paying. You will not have multiple reflection by mirrors and such. But everything will run very fast. And now do a little video, make a GIF out of it, and submit this GIF. And you can put TVs on the billboard and make the TV project your favorite shots from your favorite movie as you're walking between several sets of TVs. I think that it would be any suggestion. You'll get a few points bonus for coolness. OK, obviously, which part occludes which other part, if any, depending on where the viewer is. Once again, same slide. We have the normal that points to the outside. First step is a word that I hate because I'm vegetarian and I'm the side of the animals. Backface culling. Usually culling refers to you have too many animals of some type. In this case, you're just avoid rendering triangles that the viewer doesn't see. It depends, of course, of where the viewer is. But now when I have the normals, I can decide about a triangle that I just see its backface. And I assume here that all triangles are opaque, nothing transparent. Okay? I cannot see one triangle via another. This backface culling needs to a serious revision if triangles are not opaque. Only the part that has the normals pointing to you. And that's because this interpolation process that we define, especially if you're doing all the fancy shading, it's very expensive for a triangle, and it's pointless to make this operation per triangle that doesn't even show. So that's a very quick filtering of non-relevant triangle. To check the normal, is the normal pointing towards the viewer, for which the cosine is positive or not. Okay, so you're just looking for each triangle at this product v times n. And in a convex object, everything would be nicer if everything would be convex, invisible back face, and only every triangle that is fully toward you is fully seen altogether. If I have an occlusion with other objects, I mean, problem. Next part is a painter algorithm. And the painter algorithm, so we are done with the backface culling. We'll talk later about clipping that says there is only the regions that I care for, and it's easy to decide if triangle doesn't need to be rendered because it's not in the camera parameter right now. There is clipping, not crucial for homework 5. We'll get back to it. Depth thought is a very simple algorithm for hidden surface removal. Everybody understand what is hidden surface removal? I'm drawing the green rectangle, and the green rectangle occludes piece of the, depending on where the viewer is, but occludes piece of the part. So the painter algorithm is brilliant, for me, counterintuitive algorithm that works extremely fast in the case that it does work. And it's also important algorithm when it comes with other data structures and other settings for much larger sets, not so much as a standalone algorithm. And the purpose is to remove hidden surfaces. Pieces of the hidden surfaces, that is the one that you don't want to work. And the part that will change when the viewer will move. So what's the idea? Given the set of polygons, triangles, it's sometimes possible to sort them by depth. Here is my viewer. That would be the minus z, the direction that he's looking at. And I'll sort triangles But unfortunately, I'll draw as segments because it's 1D. Segment 1 is furthest away from the viewer. Segment 2 is a bit closer. Segment 3 is a bit closer. Why do I say that hidden surface removal is such an exhaustive task? Because you need to look at a very simple shape, triangle, and suddenly when you take one triangle and try to analyze for this triangle which pieces are visible to you and which pieces are not visible, it stopped being a triangle and stopped being simple. It can be very complicated shape, and it's very complicated to compute it. People just don't do it. There is no algorithmic approach to do it. So painter algorithm can circumvent this problem by an extremely cool idea that just said, look at the viewer from this part. So here are my triangles, S1, S3, and S2. The furthest away from the viewer is S1. That's the one that is the furthest away with the maximum depth from the viewer. What I'm going to do is to render this triangle as a whole. Every pixel in the image will be rendered as a whole. And I'll move, so I'll take on my image plane and project the black triangle, and its projection is completely black. Completely avoid any other triangle. I find out that S2 is closer to the viewer, has less depth. Confusion point, the smaller value of Z, because it's negative number, meaning it's further away from you. Okay? Standard confusion. Depth, the larger ABS value, but smaller value, the furthest away it is. S2 is closer. Now what you're going to do is to render each and every pixel on my image in blue, all the pixels that belongs to S2, the blue triangle. So I take a pixel that falls in the blue triangle, and I don't care that it used to be black region or used to be some other color of the background. Completely override it. In this case, completely render the furthest away shape, this rectangle. Next, for each and every pixel, I'll change the color to red if it falls in the next shape. For each and every pixel in the next shape, in this order, render it in this shape, and so on, until I'll get to the closest shape. Is a useful algorithm? Absolutely. If you have such an order, it works extremely well. I don't worry about which part of the shape are hidden or not. I just change the color of each object. It's just a timing of where do I change the color of a pixel to which shape. It's just a timing of does it first triangle, second, third, all the way to the closest minimum depth triangle. Give me a scenario where it's useful, really, really useful, and you don't need and there is a nice order between the shapes. I don't care about exactly what the Z values, but I care that I want to say that one shape is further away from the viewer if there is one point, I don't care which point, but as long as there is one point for which this triangle is closer to you, the viewers, than this triangle, just for one point, I'll say this triangle, independent of its orientations, this triangle is closer to you with respect to this one. Because there is one point where A comes before B. This comes before this. OK. But it's not always possible, but give me a useful scenario where it is possible. 2D games, 2D windows. Whatever the windows are, I don't need the exact Z values. But if I do have it, fantastic. And then, again, I can render each window can render each window at the right timing, and I don't care which part of it are visible, which part are occluded by other windows. Just the timing change everything, no decision. A pixel doesn't need to decide what its depth. A pixel doesn't need to decide how close it is. It's me that just feeds the triangles. Give me an example where the painter algorithm has issues. Remember, two triangles, the furthest away from you, if there is a single point that this occludes this.
Is it if one of them is like in front, that part of it?
So let's say that there are convex triangles. Any problems with rendering two convex triangles? Hint, no. If they are intersect, of course, it's an issue. But if they don't intersect,
If you have a third one where it's front and front one.
who occludes whom in this case? Who comes before whom? Right? This is closer to you than this. That is closer to you than this. That is closer than this. If you render it as a graph, you'll see a cycle over here. So either I need to break a triangle to fragments, not very effective, or use it together with other data structures. We will talk about binary space partitions, quad tree is an example, that somehow gives the painter algorithm very easily. And you can think about it as, I'll render first the background, and then I'll render the foreground. But I don't necessarily use just this as algorithm. And yeah, here are the bad cases. Right. I don't exactly what people have answered. What does work for the 20s is I don't care about all the objects, and I don't care about infinite details. I'm limited to the details of my monitors, and I let every pixel make its own decisions. I let every pixel make its own decision. It will be extremely fast. It will be extremely efficient, even if you have one CPU. But it's getting even better if you can have a few CPUs per every pixel, which has a name. GPUs comes from this application. So highlighting the remaining three objects of the Z buffer algorithms. Right now, I don't care about how many cores your computer has. What I'll do is I'll assume that my objects needs orthographic projection. Orthographic projection, meaning I just project everything orthogonally on the image plane, not perspective projections. That is, an object has the same size no matter if it's far away or close to you on the image. So I'll need an orthographic projection. And we'll study how to massage matrices, so we'll get this scenario we only have orthographic projection. And from now on, every triangle needs to be opaque. And what I'm going to do is to keep two arrays in the simplest case. Two arrays, one that I'll call the Z buffer, depth buffer, two words for the same thing, and one that I'll call color buffer, which is just for every pixel, which color it stores. And for every pixel, Pj, what Pj needs to do, I'll recycle the same image. Here in my image plane, I'll think about the pixel Pi, and this pixel wants to decide what's the color of its pixel. What is the color at the pixel Pi? What am I going to do? I'm going to scan the triangles T1, T2, T3, but it's arbitrary order. I don't assume any order that I insert this triangle by. Any order is fine. And I'll start where this pixel Pi, remember orthographic projection, just project directly on the image plane. This orthographic projection will say my color right now is black, and because I know only about T1 and what would be my depth, the depth that I'll store right here, this depth, d1, which is the depth of this pixel to the nearest object. So that might be the starting condition. And now, because the order is completely arbitrary, at this point, I will insert T5, and Pi know about T5. And P1 will ask, hey, if I shoot a ray through the pixel vertically, remember, only it's orthographic projection, the ray only goes straight. I'll hit, if I don't hit T5, not relevant for me, I don't care. If I hit this triangle T5, let me compute the distance to T5, D2, the D5, distance to T5 of this particular pixel. Other pixels will say we have different depth, different distance to the triangle. And now the pixel says, right now, I'm storing the color black. Why? Because the nearest triangle that I have seen so far is black. Now a red triangle is inserted. Let's compute the distance. But hey, this distance to the new triangle is larger than the distance that I stored, what I stored in the depth buffer. It's larger than this distance. So this pixel says, I don't care one bit about T5. At the very same time, P17 and other pixels over here will say, yes, I do intersect P5, and the distance that I had already was minus infinity. This is smaller distance, plus infinity. Let's not overcomplicate it. That's smaller, so I'll change my color right now. Sorry, I said that it's T5. What is my distance to this point of T5? Different than the previous pixel. What is my distance? It is smaller than the infinity that I stored earlier, and that's why I'll change my color to be T5. Now, the approach to the triangle is one after the other. That's sequential by definition. But how does the pixels work? It's completely independent from each other, which implies that once I figure out what the vertices of these triangles, every pixel, every fragment can work completely independently. Beautiful image. Here is how the color buffer looks like for every pixel, 2D of course. And the very same image, but now light gray represent far away object, say at infinity. Dark black represent very close to you. So this is a color buffer after inserting all these objects. And this is just a visualization of the depth buffer. You can just show as an image the depth buffer, and closer here will mean darker to you. That will be the result. So here is, and that's how you can get to such beautiful parts, the depth buffer of these shapes, the same Z buffer algorithm. You can work with very, very efficient, very fine. Just a promo of where we are going. In homework 5, you have a mirror that I'll tell you a bit more how to treat it. Essentially, you putting the camera in one place, making an image of it, and pushing it as a texture to put on where the mirror is. And texture is playing huge role in modern graphics, much more than just making a surface look like a carpet or look like it's wood. There are so many things that you're doing by mapping one texture, one shape into another. Mirror will be one example. It will be a 2-pass Z buffer algorithm. Many more applications there are. Also, all the billboards that you'll have in homework 5, what you have to play with alpha, beta, find where a ray hits. No worry about it anymore, because you will take one image. Maybe it's an image of the mirror. Maybe it's an image that appears on the billboard. You will take one of the triangles, and you'll say, I want to map V1 into this corner. V2 will be mapped to this corner, and V3 will be mapped into this corner. And the gizmos of the WebGL will take this triangle that maybe has different angles, different size than this triangle, and will wrap it correctly and put it right here. So that's how you don't need to worry about everything about the texture. So it will be relevant for the billboard. It will be relevant for the mirror and for many other applications. In homework 6, how we are cleverly using this huge power of texture mapping. Just a promo. Great work at the midterm. If you got to it without following every letter of the code of conduct, fine. I'm not here to police anybody. If you got to it all by yourself, great work. And I think that actually, I definitely believe that for all of, as much as I know, for all of them, I didn't see any reason to suspect. I mean, it looks very believable that that's what you know, and it was fine. I was very happy with the results. And if you have any issues to talk to me, I suggest for the midterm, I suggest office hours tomorrow. Thanks, everybody. Thanks, Robert.